This is chapter 3 on analytical kinematic analysis of linkage mechanisms, something that you'll be using for your project, and of course there will be homework assignments and exams out of this chapter. So really what we want to do is to learn a systematic way of stating equations and solve for position, velocity, and acceleration of links, either angular position, velocity, acceleration, or linear displacements, or of points moving with the links. We're looking here at what is called scalar robot, and if you look from above and if you make abstraction of ignore the z-axis degree of freedom, we can model it like so. So about a reference frame, fixed reference frame, x, o, y, and of course we're given OA and AB. When you do analysis, you know link lengths and the fixed angles of links in input motion. So we are given the two motor input, and we want to find the position, velocity, acceleration of the end effector as viewed from above. And we start by writing or drawing a vector loop. We associate vector to conveniently selected to each of these two links. So we have we call it R1, vector goes from O to A, and R2 goes from A to B. B again is the point that we want to find its position, velocity, acceleration given the motor input. In motor input, one would be theta 1 is function of time, so you can evaluate first and second derivatives, and then theta 2 is the second motor input, likewise a smooth function of time. The vector loop that's associated with the mechanism, it looks like so. So go from O to A, from A to B is same as going from O to B. Origin is at 0, 0. The end of the vector B, which is nothing but the sum of R1 plus R2, that is OA plus AB. It's going to be x of B and y of B. Alright, so we start with the vector loop. I say OB equals OA plus AB. And then we project this equation over x and y. And I said that OB projects as XB and YB on the fixed reference frame. And then we have for OA, before moving forward, we have a preference, and there is good reason to doing so, to measure angles from the x-axis or from a parallel to x-axis counterclockwise. If we do that, then projecting vectors over x will be always with cosine, and over y will always be with sine. So here you see this. OA projects as R1 cosine theta 1, and AB projects as R2 cosine. Of course, the angle we measure it from a parallel to the x-axis. So theta 1 adds to theta 2. Okay, theta 1 plus theta 2. And then over the y-axis, what was cosine turns to sine. So that's the position. If you know theta 1 and theta 2, you plug them in and get the xb and yb. For velocities, we take the time derivative of the position equations, and cosine turns in negative sine. Remember, theta 1 and theta 2 are functions of time, so that's why multiplication by their derivative, that is theta 1 dot, which is angular velocity at motor at O, and then for the second term, again, cosine turns to negative sine, and and the arguments theta 1, theta 2 are functions of time. And below, likewise. For acceleration, we take time derivative of the velocity equations. Alright, so sine becomes cosine, and then of course this is chain rule. We have theta 1 dot, which is function of time, and sine of theta 1, which is function of theta 1, which is also function of time. And so sine turns to cosine, theta 1 dot gets multiplied one more time, theta 1 dot, and then when for the second we have r1 sine theta 1 double dot, like right there. So theta 1 double dot, that's angular acceleration of the input motor. Again, we assume these to be smooth function of time, and it means that their derivatives exist. Of course, they could be zero. So theta 1 dot cannot be zero, but theta 2 dot could be zero, or maybe only momentarily, depending on how the input is introduced to the mechanism. For closed loop linkage mechanisms, we do the same. So we choose vectors convenient way. Again, wanting to measure angles from a parallel to x-axis or from the x-axis. And I have, so we have for this Scotch-Yoke mechanism, we have OB plus BA equals OA. We are primarily interested in the output displacement function and its first and second derivatives, that is in S of t, which is R4 on this figure. S of t, it's redundant notation. So for position problem, we say R2 cosine theta equals R4 of t, and R2 sine theta, it's R3. And so yeah, we recognize that S of t is R4 of t. And then for velocity, we take the time derivative. R4 is function of time, and then theta is function of time. So all these have been accounted for. And then for acceleration, take time derivative of velocity equations. Of course, we're interested in the S dot, S double dot, and they are right here. So S dot would be R4 dot, S double dot, that is acceleration, would be this one here. For known input, so theta should be available as function of time, then we can evaluate these equations. If we have constant rotational input, this becomes zero. Theta dot double dot is zero. So harmonic motion, cosine, sine, cosine. For the quick return mechanism, we choose theta 2 and theta 4 as shown, measure from x-axis or parallel to x-axis. We need to be given R1 and R2, and it has two isomers, two possible embodiments, as you can see, the slider to oscillate about the ground joint B, and this to be a free end that moves versus this one is oscillating. So this moves on an arc of circle. This also moves up as well as rotate. So for position, we say OA equals OB plus BA, and we project. OB projects only on the y-axis, and depending on how we select it, so we've got the arrow pointing down, and then for the velocity, rather position requires us to find theta 4 as function of theta 2, as well as r4 as function of theta 2. And as you can see, these are coupled, so I have r4 occurring on both and theta 4 occurring on both equations. So the two equations are coupled, and what we're doing is we are squaring the two equations, and we add them, and by doing so, before squaring, I isolated just the the theta 4 term on one side, and then we square. So we moved r1 to the left, and we square them, and this becomes, after adding them, the theta 4 trig function disappears. Cosine squared plus sine squared equals 1. And we obtain a quadratic in the unknown r4. Is it quadratic? No, I'm sorry, I take it back. So we just saw we can solve for r4. Really what we did was to in a sense take the law of cosines, and you don't see cosine here, you sine, but there's 1 minus cosine squared equals sine squared. Anyway, so we've got r4, and once we have r4, we can come back to any of the original equations and solve for theta 4, preferably to work with both and calculate cosine theta 4, sine theta 4, in order to apply the arctangent function, which is more forgiving, because the arguments, they don't have to be can be from minus infinity to plus infinity. If we to use our cosine function, we need to make sure that the argument is between minus 1 and 1. Okay, this is the arctangent function of two arguments. It's available on most programming languages as well as Excel, and as you can see, instead of supplying the y projection divided by x projection, I put them separate, and by doing so I preserve quadrant information. So arctangent, if I take the ratios of the two separate arguments, so minus and minus, the same as hitting plus and plus, or minus plus is the same as plus and minus. So there's some information lost by taking the ratio versus applying the y projection, x projection individually. Note that some, like Excel, it accepts the x projection and y projection, and other like MATLAB, I think they have them the other way, y projection, x projection. So read the help to make proper use of the arctangent, the two arguments. Okay, so once we find theta 4, then we can problem solve, that is, and if we want to find, for example, position of point C, whether this one or this one, we can go or write the vector loop, vector equation that's the form OB plus BC equals OC. OC projects as XC, YC. And then if for this embodiment, for this isomer, we can go O B. What would be the easy way of doing it? So it would be O A C, and we'll need to restate. So OC equals OA plus AC, and make use of an adjust angle theta 4. But the way I have it developed is for this version, I think. So OB plus BC equals OC. OB plus BC equals OC. Okay. For velocity and acceleration, you just take the time derivative of the position functions, and this yields a set of two linear equations with two unknowns. So I'm telling you now, position problem is the nonlinear one. Velocity and accelerations yield linear or sets of linear equations, which are easy to solve using Kramer's rule. And so yeah, identifying terms after taking the time derivative of the position problem yields this type of equation, where A1, 1A, 1, 2, 2, 1, 2, 2, and B1, B2 have these forms. Okay, for acceleration, we take time derivative of the velocity problem, and we get to a similar set of equation. Coincidentally, A1, 1A, 1, 2, A1, A2 are the same as for velocities. What changes are the free terms B1 and B2. And as you can see, they are a bit more involved. With some simplification possible if you have constant rotary input, that is theta 2 double dot being 0. A side problem would be to tell the orientation of a vector loop, and this can be done by evaluating the cross product. So cross product of two vectors has a k-axis component will be xb, yb, xb minus xa times yc minus yb, negative xc minus xb times yb minus ya, stated here. And if this product is negative, then the loop ABCA is oriented clockwise. If not, it's oriented counterclockwise. Again, this in order to make decisions, say you program some equations and you want to make sure that certain vectors are oriented the way you desire. Another useful mechanism that we consider was the oscillating slide mechanism, and we'll look at it. It's here. The centric one was the actuator, the hydraulic cylinder, or two-force member, and for given piston displacement S of t, we would be interested in finding theta 4 as well as its first and second time derivatives. The mechanism, as you can see, can be assembled two ways. So for the same length, R1 and R2 are given. For the same extension of the cylinder, I can pin this joint and assemble it above or below. Okay, so for the position problem, looking at the angle, so necessarily we'll be orienting vector associated with this link from C to B, associated to the cylinder, go from O to B because of this angle, the way we have it chosen. So vector loop is OB equals OC plus CB, and then we have the projections. OC projects only on the x-axis, and to solve for the unknown angles theta 2 and theta 4, that's we're mainly interested in, but we'll have to solve for theta 2 to move forward with the velocities, you'll see. So what do? We square, we isolate the theta 4 angle on one side, and or theta 2, depending on which one we want to get rid of. Since we care more about theta 4 than theta 2, we are leaving theta 2 angles or trig functions on one side. Square theta 2 disappears after adding these two equations, and what we did, we rediscovered the law of cosines, and we can solve for theta 4 using the arc cosine function. and then for theta 2, to get theta 2, we can take the ratio of the second equation by the first equation and apply the arctangent function. Okay. So this was it for position. For velocity, we take the first time derivative of the position equations and becomes a linear set of two linear equations with two unknowns. Very easy to solve. And then for acceleration, yet again take the time derivatives. We get a set of two linear equations, two unknowns, theta 2 double dot, theta 4 double dot. Only b1 and b2 are different over the velocity problem, and this is it. Slider crank mechanism. I'm sure you recognize it. This is, although in a vertical punching down, so the punch press mechanism for your project. And so we're considering the eccentric case. R1 is non-zero. We have the crank input theta 2. We want the displacement S, and so displacement S of the piston, and as function of theta 2. Could be the other way, but at this point we're assuming like crank slide. Crank is the input. Know that for a given angle theta 2, we can have two assembly modes. So I have the line of sliding. I have theta 2, say it's at 80 degrees, and I can assemble the piston or the slider either to the right or to the left. You will see it has to do with a plus minus sign in a quadratic equation. So a proper vector loop equation. Necessarily I'm going to use a vector that's OA because of this angle, and then realizing it's missing, I'm having to correct this. It's missing an angle theta 3, but theta 3 goes again from a parallel to x-axis counterclockwise, and it's shown here as I'm projecting R2, so rather vector BA, from B to A, this vector. Okay, so the scalar equations, and in order to solve them, we isolate the unknown angle theta 3 on one side, square add the equation, theta 3 disappears, and we obtain the promised quadratic in S, so S squared and S again, and then the free term. And S is going to be, again, quadratic, plus minus in front of a square root. The plus minus corresponds to the two possible assembly modes, so that's the explanation of the two assembly possibility. I have S. In order to get to calculate theta 3, I take the ratio of this second equation by this equation, and apply the arctangent of two arguments function. So position fully solved. I know theta 3. I know well, S dot it should be given. No, I'm sorry. S dot is the desired input or desired output that we need to calculate. Okay, so we get, as is expected, a set of two linear equations, two unknowns. Here are the coefficients, which can be easy to solve, and then taking the second type derivatives, it gets us again a set of two linear equations, two unknowns, a11, a21, a12, a22 are given. Free terms b1, b2 differ from the velocity problem. Okay, so for your project, you have to state the equations for the slider crank, or crank slider input is the crank, when the piston moves vertically, that is up and down, not horizontally left and right. but steps would be the same. Okay, for the 4-bar mechanism is the most involved of the simple mechanisms, and we're assuming the input to be at theta 2. We know R1, R2, R3, R4. If I have theta 2 given, I want to find theta 4. For a given theta 2, as you can see here, I have two possible assembly modes. One as shown to the left, the other one would be like flipped or mirror about line AC. Here too we're going to see a plus minus in front of a square root. So for position problem, we are taking the vector loop OA and looking at the angle. So we chose theta 3 as shown. It means that I need to make use of an angle of a vector from A to B. As theta 4 is selected, I need to use a vector CB. So here they are. OA plus AB equals OC plus CB. And then project them on the X and Y axis, again choosing the angles as shown. X-axis projection will be all cosine, Y-axis projection will be all sine. Of course, OC vector does not project over the Y-axis, that's why it's just by itself R1 here. In order to solve it, we do the same. We separate on one side an unknown angle, theta 3 this time, and we squared two individual equations, and then we add them. Theta 3 disappears after summation, and so what we're left with is an equation like this one, where the unknown is theta 4, the output link angle, and we arrange it of the form A cosine theta 4 plus B sine theta 4 equals C, where A equals, B equals, and C equals, again identifying terms. Equations of this form have solutions to arctangent of B plus minus A squared plus B squared minus C squared over A plus C. So plus minus in front of a square root, reminiscent of a quadratic. And indeed, you get a quadratic by replacing cosine theta 4 with its half angle equivalent, so it would be 1 minus tangent squared of theta 4 over 2 over 1 plus tangent squared of theta 4 over 2. Sine would be 2 tangent of theta 4 over 2 over 1 plus tangent of theta 4 over 2 squared. Okay. Anyway, so plus minus, the sign corresponds to either this or this assembly mode. You choose just one, same as earlier. I should have mentioned that. So the plus, and this is an alternative form using arctangent of two argument function again. So you choose either plus or you choose either minus, and you stick with it for the entire analysis. Question is, which one is my solution? So you can go back to the discussion with orientation of vector loops, or look at some values and see if they match your expectations. In terms of, you know, the angle being around, say, 120 degrees rather than being over 180. Okay, for velocity problem, we need to have the position problem fully solved. And that is, we need to go back and solve for theta 3 off this equation. You take the ratio, apply arctangent, and you find theta 3 from these two equations. One theta 4 is known. So velocity, take the time derivative, and yields a pair of two linear equations as two unknowns. Easy to solve, Kramer's rule. And then for acceleration, you take velocities and evaluate the time derivative of the velocity equations, and you get the same linear equations with two unknowns, with b1 and b2 differ, a11, a12, a21, a22 being the same. Okay, we looked at points attached to moving links for the quick return. we can have, for the case of a 4-bar, slider crank could be the same if we want to study the motion of a point on the coupler, for example. I can specify a point moving with link AB either by giving fixed angle alpha and length R4, or I can give R5 and R6. It is specify D in a reference frame that's moving with link AB with origin of A, X, from A to B, Y perpendicular up. Alright, so the way it's shown here, to get D, I write OD equals OA plus AD. And OA is we need to make use of theta 3 at some point, because again we project or we need to know an angle relative to the horizontal axis, so we'll have R5 cosine of theta 3 plus alpha, and you can see them here. And then, you know, first for the Cartesian, using the local reference frame with R5 and R6. So what do we have? R5 and R6. The vector loop is OA AE plus ED. So I have R2 R2 cosine plus R5 cosine theta 3 plus R6 cosine of theta 3 plus pi over 2. So there's looks like I need to change a 6 into 5 and 6 into 7, so this should be, sorry for this, 5 and then 5 again, and this is 6. I don't know how I got it. 6 and 6. 6. Okay, so position solved. If you want velocity and acceleration, you need, of course, take first and second time derivatives. Position of the basic 4-bar should be, velocity and acceleration should be known, because there will be theta 3 that occurs in both instances. Okay, if we have multiple loop mechanisms, like this watt linkage, a 4-bar in series with a crank slider or rocket slider, we need to take care of the first loop first, and then write the equation for the second loop, and have the output link of the first loop of the 4-bar input link of the second one. Another possibility is to have a 4-bar and the coupler curve is moving a via connecting rod, a piston along a fixed distance. And how do you specify the fixed distance? A point and an angle beta, so I need to know link length, fixed angle, length again, angle beta, and the point about which or through which the line of sliding is running. Same here. So I know P, its coordinates, and angle beta, and this is a fixed direction along which the slider moves. I'm just giving the vector equations, and again, what connects them here would be the crank slider loop was the input, the output link for the 4-bar angle minus 6 angle alpha. Here there will be a XD YD driving the connecting rod and moving the slider. I may be interested in either coordinates of E or the distance displacement PE for the on the second loop. Okay, and I guess this is it. I have some exercises. We'll do some of them in a different recording. Thank you for watching.